Today's goal is to solve exponential equations algebraically. Keep in mind, solving means we're looking for solutions, x values that make the equation true. And exponential equations are equations that look like a times b to the x is equal to something. By exponential, we mean that the variable is in the exponent. And algebraically means we're not going to need a calculator to do this. So let's back up a little bit to talk about the general strategy and why we need this strategy. In previous units, you solved equations with exponents by using roots. Like if you had an equation such as x cubed is 64, you would take the cube root of both sides, and we know that the cube root of 64 is 4. But actually, this equation wasn't exponential because the exponent was not a variable. That was a cubic equation. So we need a new strategy. Sometimes we can solve exponential equations like 64 is 4 to the x. Just by using our knowledge of exponents, well, we know that 4 to the third power is 64, so x must be 3. But what if you're trying to solve an equation like 64 is 5 to the x? Well, 5 cannot be put to some integer power to get 64, so how would we figure out the decimal that best tells us 5 to this power is 64? We'll need logarithms. And logarithms allow us to write a fact in a different way. This is something you've been doing for years. Like, you know that 2 plus 3 is 5, therefore 5 minus 2 is 3. And 2 times 3 is 6, therefore 6 divided by 2 is 3, right? You're just writing the same fact in different ways. 2 cubed is 8, therefore the cube root of 8 is 2. And today we'll rewrite exponential equations as logarithmic equations. In fact, 2 cubed is 8 is the exact same fact as the log base 2 of 8 is 3. You're just rewriting it in a different way. More generally, if you can write an equation base to the power exponent is equal to the argument, you can rewrite it as the logarithmic equation, the log base b of the argument is equal to the exponent. Some people remember this by thinking this is log base b of a is e. It spells out bay, right? You love logs so much that you can make them your okay, let's start out by getting comfortable with logarithmic expressions just by evaluating. So we get a sense of like, what do these numbers represent? To evaluate, you'll need your calculator. You're going to type the math button, which is highlighted right here. It's right under second. And that'll take you to a menu that looks like this. You're going to keep scrolling down until you get to the option that says A. It'll be below here. Option A, log base. It'll bring up a menu like this, and then you can use your arrows to type in the number of the base and the value of the argument. So for example, grab your calculator and type this in, log base 6 of 36. Notice that the base is written as a subscript. It's a number very small, slightly beneath the line of text. And 36, the argument, is written in a normal size. It's not an exponent. It's not small and written like up here. The argument is written in normal size. Okay, so log base 6 of 36 should give you 2. Well, that makes sense because 6 squared is 36. If we rewrite this fact as an exponential equation, we can see why the log base 6 of 36 is 2. And if you type in log base 25 of 5, you should get 0.5. And if you type in log base 25 of 2, here's an example of one that's going to give you some decimal approximation about 0.215. It's not an integer value because this is saying that 25 to the power 0.215 is 2. Well, that makes sense. You can't put 25 to an integer power. It's not like 25 squared or 25 cubed is going to give you 2. All right, let's get a little more practice converting before we solve. 6 squared is 36. This is my base is 6, since that's the number holding up the exponent. Of course, 2 is my exponent, and that would mean that 36, by default, it's the leftover, guys, the argument. So we're going to write this as log base b, so base 6 of 36 is 2. This is rewriting the exact same equation, the exact same fact, in a different way. Okay, square root of 49 is 7. Well, this doesn't appear to have an exponent, except we remember from Unit 4 that 49 to the 1/2 is exactly the same thing as the square root of 49. And that makes it a little bit more clear what my base is, what my exponent is, what my argument is. So I have the log base 49 of 7 is 1/2. Now, you don't have to use parentheses around the argument. You could also just write this as log base 49 of 7 is 1/2. But you'll see in the next example why I think the parentheses help separate the argument from anything that's not inside of the logarithm. Okay, 9 to the 0 is 1. Again, we've got our base is the thing holding up the exponent, and the argument is the thing on the other side of the equation. So we have the log base 9 of 1 is 0, and likewise the log base e of 1 is 0. We know that. Anything to the 0 power is 1. Okay, now it's time to solve. We'll give exact solutions unless otherwise prompted. So we have an exponential equation. We can't use like a bth root to get rid of it, because what would you do with that, right? The only strategy we have for getting a variable out of the exponent is to rewrite the exponential equation as a logarithmic equation. So we're going to write this as log base 3 of 17 is b. And we're actually done. This is our solution, the number that makes the equation true. Now, if you type this into your calculator, you'll get some decimal approximation, and then try it. Try 3 to that number, whatever it is, and make sure that you do indeed get 17. And when you type this log base 3 of 17 into your calculator, you get some decimal that you would have to round at some point, or your decimal is already rounding it, because in your calculator screen, right, there's only room for so many numbers before they had to round at the very end. So if we want an exact answer, this is the exact answer, log base 3 of 17. Okay, let's take a look at b. It's slightly different because the exponent is not yet, or the base in the exponent, this guy, is not yet alone on one side of the equation. Our conversion to logarithms requires that the only terms you're dealing with are a base, the thing holding up the exponent, an exponent, it's okay that it's an expression in this case, and an argument. So it's like I've got extra stuff. We can isolate the base by adding 5 to both sides. So now we have e to the x minus 1 is 10. Now we can convert to a logarithmic equation. And all we have to do is make sure we have isolated the variable at the end. Now here, I really want to emphasize that the 10 is in parentheses, the 1 is not. Because if you type into your calculator this expression without the parentheses, it may think that your answer is log base e of 11, which is a totally different number. This is not the solution. 1 is not a part of the logarithmic expression. That's why we use parentheses around the argument to really emphasize 10 is inside of the log, 1 is not. And one final question for you today. We're going to solve this equation and round to the nearest hundredth. So that means we'll need a calculator at the end. Again, our strategy is we can rewrite this as a logarithmic equation to get the variable out of the exponent as soon as we've isolated the base and the exponent. So I need to move the -6, I need to move the -3. We've been talking about this a little bit, but if you're evaluating, you go in this order. If you're solving, you're taking things away, so you go in the opposite order. So let's add or subtract first. That means we're going to move that 3 first. I'll rewrite this. Now we're going to multiply or divide. You can leave it as a fraction, you can simplify it if you want, or turn it into a decimal. It's sort of your choice. Now we have the base alone on one side of the equation with the exponent, so we can convert to a logarithmic equation. So log base e of 20 over 6 is 8n plus 8. Now I just need to finish isolating the variable. So again, we're going in the reverse PEMDAS order since we're undoing things that have been done to the variable. So we'll subtract. We have log base e of 20 over 6 minus 8 is 8n, and then we'll divide. We'll divide each term by 8. So we have log base e of 20 over 6 divided by 8 minus 1 is n. We would box this in if we wanted an exact answer, or if it didn't specify whether we wanted an exact answer or an approximation. But since the question asked us to round to the nearest hundredth, we're going to grab our calculator, press the math button here, scroll down until we get log base, option A, and type this expression into our calculator. When you do so, you should get n equals negative 0.85.